All right, guys, what we're going to be looking at here is an example from 2019 where we are going to be creating like a Taylor series of some sort. Okay, so just be aware as we look at this one. This is a little bit different, but it's not awful. So let's just take a look. Okay, it says a function f has a derivative of all orders for all real numbers x. A portion of the graph of f is shown above, along with a line tangent to the graph of f at x equals 0. Select the derivatives of f at x equals 0 are given in the table above. So I have this tangent line right here. Here's my original function. I don't know what that is. And then I know what different derivatives are. So I can see the second derivative is equal to 3. The third derivative is equal to negative 23 over 2. The fourth derivative is equal to 54. So we have some information here. You'll notice it doesn't tell us the first derivative. Now remember, the first derivative just tells us the slope of the tangent line. So really, if I needed one, and we will need it, notice this goes down 2 over 1. So my slope is negative 2. So if I plug in 0, okay, and I find the slope of that tangent line right there, the slope of that line is negative 2. That'll help us out in just a second. Okay, and we also need to know, well, we'll just look at it. Okay, so it says write the third degree Taylor polynomial for f about x equals 0. Well, in order to do that, since we're at x equals 0, I need to take my first term, which is just where I'm going to start drawing this. That's the y value when x equals 0. So my first one is 3 plus, then, since I'm centering it at 0, I need my first derivative, which we found on the last slide was negative 2. So I'm going to go negative 2 times x minus 0 to the first power. I'll just write it all out, x minus 0 to the first power, because we're centered at 0 over 1 factorial. Again, we take the derivative, and then we just write it out like that. Then we go plus the next term. That's going to be the second derivative when we plug in 0. That's 3 multiplied by x minus 0 squared divided by 2 factorial plus I've got the 3 is negative 23 over 2 times x minus 0 to the third power divided by 3 factorial. Now, I know that looks like a mess, because it really does, but that is our third degree Taylor polynomial. If you look at it simplified, it kind of simplifies down to this, and we'll need this later in the problem, so that's why I'm simplifying it. So I get 3 minus 2x plus 3 halves x squared plus, or minus, 23 over 12 times x to the third. Okay, so there's my polynomial, and either one of those answers works just fine. Now, letter B says write the first 3 non-zero terms of the Maclaurin series for e to the x. Remember, e to the x is just 1 plus x squared over 2 plus x squared over, or x to the third over 3 factorial, on and on and on. But it just wants the first 3 non-zero terms. So there's my e to the x for that Maclaurin series. Then it wants me to write the second degree Taylor polynomial for e to the x multiplied by f of x, okay? Well, it wants a second degree Taylor polynomial. What that means is I am going to multiply these two things together, the e to the x and what I got for my Taylor polynomial, or at least the first part of my Taylor polynomial, or my Taylor series for what I got previously. I'm going to multiply those together, but notice it only wants the second degree Taylor polynomial, which means I only need things that are raised to x squared or lower. The way that I'm going to find this is I'm going to multiply the 1 into all of those things. So I get 3 minus 2x plus 3 halves x squared. Then I'm going to multiply the x into everything. So, and again, you can keep multiplying it out. But I only want the things that are x squared or lower to make my second degree Taylor polynomial. So I get plus 3x minus 2x squared plus 3 halves. Oh, I don't even need 3 halves x to the third. Then I'm going to multiply x squared in there. Okay, so I'm going to get plus 3x squared divided by 2. Once I have that, that's all I need in this problem, and I'm all done technically. Now, if you do simplify that down, you get 3 plus x squared. And I mean, this is the non-simplified version. The simplified version, again, we're going to need it in just a second. But that is my answer for letter B. Letter C, let h be the function defined by the integral from 0 to x of f of t dt. Use the Taylor polynomial found in part A to find an approximation for h of 1. So what it wants us to do is it wants us to do the integral from 0, not to x, but we're plugging 1 in. So I do the integral from 0 to 1 of that same Taylor series that we created in part A. Okay, so I've got this right here. So I want to, what it wants me to do here is it wants us to do this by hand, take the antiderivative, so I get 3x minus x squared plus 3x to the third minus 23 over, well, that's not right. I wrote, let's see, so that's x to the third. Yeah, that's, nope, just kidding. This is 1/2 x to the third. I apologize. Then this is 23 over 48 x to the fourth, evaluated from 0 to 1. So I get 3 times 1 minus 1 squared plus 1/2 times 1 to the third minus 23/48 times 1 to the fourth. Then I'm going to subtract off all that stuff with 0 in it, so it's just going to go away. If you need to know what that is, that's just 97 over 48. That's our answer for letter C. Letter D wants to know, it's known that the Maclaurin series converges to h of x for all real numbers of x. It's also known that the individual terms alternate in signs and decrease in absolute value to 0. So it's saying it's an alternating series. Use the alternating series error bound to show the approximation found in part C differs from h of 1 by at most 0.45. Now remember, anytime we're using an alternating series error bound, we just use the next unused term to do that. So our polynomial went up to x to the third, so I need to make x to the fourth. That's 54 times x minus 0 to the fourth power over 4 factorial. And 4 factorial is 20, let's see, that's about 4 times 3 times 2 times 1, that's 24. So I get 54 over 24 times x to the fourth. So that's my next unused term. But what we have to realize is we took the integral to find our new series in part C. So I need to take the integral of that one as well from 0 to 1. So I'm going to get 54 over 96 x to the fifth from 0 to 1. So I plug one in, I get 54 over 96. And 54 over 96 is, if you like simplify that down, that is 9, let's see, oops, excuse me, 6 goes in both those. So I get 9 over 6 goes into that 16 times. 9 over 16. I did something wrong here because it should be 9 over 20. What did I do wrong? I probably multiplied something together wrong. Anyway, you should have gotten 9 over 20. I don't want to take the time to find where I made my mistake there. But that is equal to 0.45. That's at most, because it's the alternating series error bound. It's really bothering me where I got this wrong. What did I do? I see it now. I apologize. This 96 is actually 120 because I needed to multiply by 5, not by 4. So that does equal 9/20. There's the 0.45. Again, I apologize for that. That one was a little bit tricky, not setting it up, but like figuring out that I'd use the next unused term and take the antiderivative of that one. Anyways, if you have any questions about that or any of the other problems that we've looked at, please let me know.